Hello students, this is Mr. Allen. Today we are going to look at a very important differentiation rule known as the chain rule. Our objectives today are to find the derivative of a composition of functions using the chain rule. That's our primary goal. We're also going to look at the general power rule. We want to be able to simplify derivatives of functions using algebra. And finally, we're going to look at the derivatives of some trigonometric functions using the chain rule. So far, we haven't got to the chain rule, but we've actually been using it, and you probably didn't even realize it. This rule deals with the composition of functions and adds a surprising versatility to the rules we've discussed in the previous two sections. So remember, a composition of functions might be something like, f of g of x. Okay. You also sometimes see it written like this. This would be a composition of functions. Hopefully you remember that from Algebra 2 and in pre-calc. So here are some examples of equations that would not require chain rule, because if you look at them, you can see that they really don't look like a composition of functions. But if we look at these particular examples, we can see that the chain rule is probably going to be necessary because this is a composition of a square root function with an x squared plus 1 function inside of it. Here we can see that we have the sine function with the 6x function inside of it. So the chain rule is basically how you handle composition of function derivatives. It states that if y changes, dy du times as fast as u, and u changes du dx times as fast as x, then y changes dy du times du dx times as fast as x. So this is the rule that we're going to build on in this particular section. Consider the gears constructed in the diagram here to the right. So we can see that there are three gears, and notice that the second and the third gear are on the same axle. The first axle revolves and it drives the second axle, which then turns the third. So if the first axle or the first gear is turning this way, then that means gear 2 and gear 3 are turning that way, and then gear 4 is turning this way. Now the thing to note though is the radius of these axles. So this is a composition of functions. So if we want to figure out what's going on with the relationship from gear 1 to gear 4, we would want to look at the three axles and how they're related. This would be the formula that we would use to find that rate of change. dy dx would be equal to dy du times du dx. So before I move on to the next slide, if we look gear 1 to gear 2, that ratio is 3. So dy du would be 3. The ratio of gear 3 to gear 4, that is 2. So that would be 2. That's the rate of change of those gears. Therefore, dy dx would be, that's correct, dy dx would be equal to 6. So here is the chain rule. The chain rule says that if y is equal to f of u, which is a composition of functions, written like this, the u would be the inner function, u is the g of x, then the derivative of the function with respect to x, in other words dy dx, would be equal to dy du times du dx. Equivalently, you'll also see it written like this. So notice that on this second derivative formula, the f of g of x, when you do the derivative, you do the derivative of the outer function, leaving the inner function alone, times the derivative of the inner function. I'm going to try to do a very simple example to kind of explain to you. First of all, I'm going to actually show you how to do it incorrectly, and then I'm going to show you why it's incorrect. So you guys should all already know what the derivative of this is. In fact, let's just talk about that. If I asked you what y prime was, my guess is you would all very quickly say that it's 6x to the 5th by the power rule. We know that. That would have been in section 2.1 or 2.2. 2 would have been the shortcut. Anyways, we know that that's the derivative, but let's think of this function in a different way. Instead of thinking of it as x to the 6th, let's think of it as x to the 3rd quantity squared. So what I'm trying to do is make this look like a composition of functions. So you could think of this as f of g of x. Or if you want to think about it this way, another way you could think about it is you could think about this inner function as u, and then this outer function as f of x. So if I said, what is y prime? Now, again, we already know what the answer is. It's over here. Intuitively, I think a lot of students would think the answer is going to be do the derivative of the outer function. So notice I took that 2 and I pulled it to the front. And then do the derivative of the inner function, which would be 3x squared. And then, of course, we simplify that. We get 6x squared. Now, clearly, we can see we got the same coefficient, which is nice, but we got a different power. We got x squared. So this is incorrect. In fact, let me just go ahead and mark that out. This is incorrect thinking. This is not how this works. Now let me do it correctly. Let's do it in green. So I'm going to write, instead of y prime, I'm going to write it as dy dx. The formula is dy du times du dx. Okay, so let's go ahead and do that now. So what we're going to do is, again, we're looking at it written in this way. We're going to do the derivative of y, that's like the outer function, that's the f function with respect to u. In other words, we're going to just pretend whatever that inner function is that's u. U is literally this x to the 3rd. So if I asked you what is the derivative of u squared, you would probably tell me that it's 2u to the 1st. But remember, u here is x to the 3rd times. Now, so we've done this piece right here. We just did dy du. By the way, that's to the 1st power. That's not a factorial. Now we're going to multiply it by du dx. So now what we're going to do is we need to do the derivative of u with respect to x. So what is the derivative of 3 or x to the 3rd? Well, that'd be 3x squared. So now when we clean this up, we get 2x to the 3rd times 3x squared, which is 6x to the 5th. This is the result that we wanted. We see that up here. This is an example of the chain rule, okay? And again, I do this example only to make it very simple and easy for you to see we already knew what the answer was before we began, okay? You do not have to do a problem like this with the chain rule. It's just to illustrate the chain rule. So here are several examples of decomposition of a composite function. And what this is saying is, I've noticed none of these are derivatives. What this is, in order for you to use the chain rule, you need to think about how could this function be written as a composition of functions. So in this case, what we're going to do is we're going to think of the outer function, if you will, as being a quotient. In other words, it's 1 divided by u. Then the inner function, the u function, that'd be this x plus 1. The second example here, sine 2x. The outer function is the sine u. The inner function is 2x. So a good way to think about this is if you knew what x was, if I said x was 1 in example B there, the first thing you would do to 1 is you would take it times 2, and that gives you 2. And then you would take that and you would put that in the sine function, and then that would give you whatever the sine of 2 is. And of course, I don't know what that is off the top of my head, but that's how that would work. So the inner function is what happens to the variable first. And then, of course, we've got some more examples here. I would note that these two guys are pretty important to understand order of operations. Tangent to the 2 power x is the same thing as tangent squared. That's why the inner function is tangent and the u squared is the outer function. So this is actually a very important slide to help you set up your chain rule problems. One of the most common types of composition of functions is y equals u to the x to the n. We've already seen an example of that. This is referred to as the general power rule. We can use the chain rule in this case, and this is just a specific case of the chain rule. And here's the theorem. So again, this is obviously important stuff. So that if I have u of x to the n and I want to do the derivative of it, you basically can just use your power rule. Okay, you can just use your power rule. So for example, if I had, y equals, let's just say x squared. Oh, that's not a great example. X squared to the third. Okay, so this is the same thing we did earlier. So to do this, y prime, again, you're going to bring the n to the front. So that's going to be 3. You leave the inside alone. You subtract 1 from the 3 and you get 2. Then you have to multiply it by the derivative of the inside. So you got to multiply this by 2x. And then so you'll end up getting 6x to the 5th, which again, we've already seen that. I apologize, I just redid the same example. All right, so this one I've already got worked out ahead of time, so this will go a little bit faster, and it's typed, so it's neater than my handwriting. So let's say I want to find the derivative of this function. It's a little bit more complicated than when we did before, but it's just polynomial, so this is no big deal. So you want to identify, here's the inner function, so that's the u, and then here's the outer function, so that's like u to the third, okay? So u is that inner guy, that's the 3x minus 2x squared. F of x is u cubed, which is what we just said. Then by the generalized power rule, we can simply take this 3, that's the n, and put that in the front, and then reduce that by 1, leave the inner function alone, and then take the derivative of the inner function. When we do that, we get 3 times the quantity 3x minus 2x squared, and then the derivative of this inner function is 3 minus 4x. And that's our final answer there. I mean, you can distribute this, but that's really not necessary. That's your y prime. Okay. The next 3 examples illustrate some techniques for simplifying the raw derivatives of a function involving products, quotients, and composites. And again, I've got these all typed up, so they'll be nice and neat. So let's start with product. So here's a product of 2 functions. So we've got x squared and then times the square root of 1 minus x squared. So this is going to be a combination of chain rule with the power rule. The chain rule with the product rule. And just a reminder, for the product rule, that's 1d2 plus 2d1. Okay, we did that in section 2.3. So the first thing that we could do here is the following. Notice this is still f of x. I have not done a derivative yet. I have only simplified, I've rewritten this square root as a 1/2 power. Now I'm going to go ahead and do my product rule, which I just mentioned here. So I've got to do 1, which is this, times the derivative of 2, plus the second thing times the derivative of the first thing. So now we can just use our power rule and our chain rule. Notice that here we're having to use the chain rule. So we've got the 1/2, the negative 1/2, and then the negative 2x, which is the derivative of the inside. Over here on this part, we did not need to do the chain rule. We're just going to simplify this now using the distributive property. We're going to factor out. Notice that here we have 1 minus x squared. We also have a 1 minus x squared there. So we can factor out. Then we can clean it up some more. So here's our f prime. Here's our final answer. Okay. Now notice, even though this is a pretty straightforward problem, there's definitely some algebra involved and definitely some calculus. We had to use the product rule. We also used the general power rule, which again is another way of saying the chain rule. All right, let's look at a quotient. Remember the rule for quotient. I won't write it down, but it's actually, you know what it is. So again, there's a mnemonic device for the product rule. There's a mnemonic device for the quotient rule. And I'd like you to maybe think about what that is right now. Hopefully you're thinking something about low things and high things. So here we're going to use the quotient rule, and we have to use a chain rule because of that bottom function, the function in the denominator. So first thing I'm going to do is rewrite this. So notice that I've changed the radical to the 1/3 power. Now we're going to do our quotient rule. So for example, notice the denominator is the same denominator as this one. It's just squared. And then up here, we've done some chain rule and some other things, some non-chain rule steps. Now, in the numerator, we have some common factors. You'll notice that there's an x squared plus 4 to the 1/3 here. There's an x squared plus 4 to the negative 2/3 there. So we can factor that out. Now, again, I want to caution you guys, one of the biggest difficulties that students have in calculus class isn't the calculus, it's the algebra. And so we can just clean this up some more, and here's our final answer. Here's f prime. And I wouldn't go any further than that. I mean, if you want to write it as the third root or something, you could, but that's good enough. I'm going to look at some trig functions in chain rule now. So no big surprise, you know that the derivative of sine x is cosine x. So if I do the chain rule, then it would be sine u times cosine u times the derivative of whatever u is. So notice that all these rules for the trig functions are exactly what they were when when we were just talking about like sine x and all this. It's just now the rules are all the same. It's just now you have the additional y prime or u primes on the outside. Let's look at one more example here of the chain rule, and this one really shows why we call it the chain rule and not like the composite function rule. And the reason is because there's going to be a chain of events that happen here. The first thing I'm going to do is I'm going to rewrite this expression, clear that off here. So I'm going to rewrite this expression as sine quantity 3x squared. So this is, again, I showed you in a previous slide, these two things are equivalent. I'm just writing this because I want you to see that there are 3 levels of things going on. If you knew what x was, the first thing you would do is take it times 3. Then you would do the sine of whatever that is, and then you would square it. So in order to do this one, instead of having f of g, it's going to be actually f of g of h of x. So we're going to have to unwrap this chain, if you will, to get our derivative. So I'm just going to do this. I'm going to kind of do most of these steps kind of in my head, but I'm going to explain as I go. So remember, we're going to work out all the way into x, okay? So the outermost function is this squaring function. So the very first thing I'm going to do is I'm going to take this 2 and I'm going to bring it to the front, and then I'm going to leave those parentheses or those brackets there because this inner function does not change. This is just what it is. So that was the generalized power rule. So that's step 1. Step 2, now I've got to do the derivative of this thing, the sine 3x. Well, the outer function there is sine. So what is the derivative of sine? Well, the derivative of sine is cosine. Now again, I'm going to leave the inner thing alone. So that's cosine 3x. And then finally, you have to do the derivative of the innermost thing. So what is the derivative of 3x? Well, the answer is 3. So in this example, y prime is equal to 6 sine 3x times cosine of 3x. So all I did is I took the 2 times the 3. So that's the derivative. That's why we call it the chain rule, because there was a chain of events that happened there. And it could be more than 3 steps. It could be multiple steps. Finally, here's just a summary of some of our differentiation rules. Here are some of the general differentiation rules. For example, here's a constant multiplier rule. I'm not going to read through those. Product rule, quotient rule, etc. Here's some basic derivatives of algebraic functions, like the derivative of a constant is 0. Here's our power rule. Then we have some of our trig derivatives here. And then we have our chain rule down here. And I'd also like to note that the derivative of e to the x is e to the x. And the derivative of the ln of x, the ln of x, that's ln of x, is equal to 1 over x. There's a couple of additional ones I should probably throw in there. I think we're going to stop it there.